All right, so here's the class crap. It's up there. Normal stuff. Quizzes, 20%. Homework, 40%. Midterm final, 20%. Same as usual. Questions?
Somehow the book ended up on Slack.
Oh, the book's on Slack?
Yeah.
All right. So required text for the class. You can order this or get it wherever you want. Where's this guy?
Passed it. The Linux programming. Whoa.
They passed it?
Yeah. There it is.
Where?
No.
Ah, the Linux programming interface. So we're actually going to do this class a little bit differently than I've done it in the past. The past I've taught it as completely a compiler's course. This time I found this book and looks pretty legit. We'll find out how legit it is actually once we go through it. But we're going to kind of do it as a Unix operating system, Linux operating system, kind of almost like hacking type course. There'll be a compiler component. There'll be a systems programming. Systems programming in general is how do you interface with an operating system, and compilers is kind of at the heart of that. So we'll be talking about it in a very similar way, but I think we'll maybe be doing some additional practical stuff. So hopefully it's, I guess, kind of fun. It'll definitely be impossible. We'll be writing a lot of code in C. Some very old language. So we'll start talking about some of this stuff today.
Are you using Kali or just like brain over?
I haven't even decided what we might use a thing called Cloud9 that actually hosts Ubuntu. But I'm going to see how well the stuff works just on the Linux console, and we'll go from there because that's technically BSD Unix, so it should be POSIX compatible. And we'll talk about that stuff today. All right. Oh, wait a minute. This is from the last time I taught it. I need today's. There we go. All right, and I guess I need to reference the text real quick. I left my copy in my office.
It's like emulating software, as long as you have a real copy, right?
All right. How many of you are taking the ethical computing? Manouche. I did not.
This is the perfect complement to the ethical computing because it shows you everything that you're not supposed to.
I did not distribute this. My hands are clean.
Well, you put it up on video, you technically did.
Well, that's true. Just flip through real slowly. It's the last thing I need is another copyright strike.
You're the expert. Is this
You went to school. Did you forget everything already?
They only ask you 8 questions to complete Google's Google YouTube copyright school. And they say that we'll take it down after 6 months. That the strike will be gone after 6 months. But I have access to my account.
He's officially has bad standing.
So, are you creating another account?
No, I have access to it now.
Oh.
I had to go to school in order to get access. I passed.
That's a good thing. Most challenging course you ever took?
Alvin would exactly flag somebody putting an entire book on a YouTube video.
Well, I think it would be you'd have to have somebody stumble across it visually.
Right.
So I think they're doing all their audio filters in order for
Well, somebody just like says the name of the book.
Yeah. All right, so we'll flip back and forth between the book and stuff. So I'm going to kind of start off talking about this. So tell me what you guys know about Linux and Unix and that kind of stuff. What does that mean to you when somebody says Unix or Linux? Who? Poor man's operating system? Okay, fair enough. Yeah.
Built by a community, open source.
Okay. Linux, open source. Unix would also be, it's accurate to say it's built by a community. So Unix was kind of a operating system built by a bunch of scientists, guys, in kind of collaboration, so that, you know, they could best take advantage of kind of early computing devices. So we're talking late 60s, early 70s. It's kind of the whole evolution of those operating systems. So Unix came first. Linux was, I guess, masterminded by a guy named Linus Torvalds, who actually I saw it glancing at the book. I think he was born the same year as the first version of Unix came out. It's kind of interesting trivia, I guess. But in any case, Unix was specifically written for specific hardware initially. Okay, so that means it was written in assembly language. So that's this initially written in assembly. So tell me what you know about assembly language. We've talked about that in some various courses. What does that mean to say that this operating system was written in assembly?
Extremely specialized.
Okay, that's a true statement. So in what way? Well, like, what if I were to look at the source code for it, what would I see? What kind of stuff would I see?
CPU instructions.
Okay, so I'm talking, with assembly, I'm talking directly to a very specific CPU. I'm talking directly to hardware, right? All right, so there is no like gray area middleman type thing there. So it's like I'm giving instructions to somebody in Spanish. And those instructions could not be easily translated into something else. All right. I'd have to rewrite it. I have to rewrite it from scratch, or at least largely from scratch. We don't have a tool that allows us to have it go over to something else. So initially, these operating systems were very proprietary. So imagine that scenario where you're writing an operating system like, you know, the first version of Unix, completely in assembly, which would have been just a task. Okay, even though, you know, I think we could probably assume that the original early operating systems probably were not nearly as beefy as today's operating systems, right? Still, if you had to write that entire thing in a low-level language, we can imagine that would probably be a pretty big task. All right, so not fun writing that anyways, and also it was very, very machine-specific, architecture-specific. So that's why it was written initially in assembly language. Now, when you hear C programming language, what does that mean to you? I don't know. Tell me, where does C fit in your world of programming languages? Most of us in here have not written, at least not very much, C code. We've written in languages that are derivations of C, so we kind of appreciate maybe where our language came from. But what does C mean to us? Is it this old, useless language? What was C designed for? Okay, so it's a high-level language. So right off the bat, we kind of talk about what we talk about fixing this problem we just discussed. That, well, if you're writing in a low-level language, first of all, that's not very much fun, regardless of what the assignment is. And secondarily, it's not portable, right? Assembly language is not portable. If you're going to write something in assembly natively, it's for that architecture. Could you use that as a paint by number to write for another architecture? You could at least use it as a guide. It wouldn't be direct. You wouldn't be able to just literally copy it directly and make the equivalence. There might be some architectural differences on the other architecture that might drive you to have to do certain aspects of it differently. But it would be fair to say that assembly is not portable. Okay? So that's one problem a high-level language in general solves. So C came out kind of around the same time as Unix was, let's say, becoming popular. And it was originally designed to be a language for writing operating systems with the mentality to solve this one problem. How can we write an operating system, whatever that means, whatever it means for something to be an operating system? Right now we're talking about it in the context of Unix. What does it mean to write that in such a way that it's, quote, platform independent, or at the very least, more platform independent than the assembly version of this? Okay, we're going to say the assembly version is extremely platform dependent. All right, so why write an operating system in C so that the OS is portable to different architectures with, let's just say, minimal work? Because we do need to keep in mind that today, things are more compatible across the board than they really ever have, than they've ever been. So we go back to 1970, even with this idea of them designing something to be portable, our computer hardware wasn't compatible back then. You know, you couldn't just put any circuit board into any computer. So there was incompatibilities all over the place. So at the very least, this made the problem less of a problem. But the problem still existed. Okay, so how would a high-level language like C allow us to write an operating system that would be more portable? What are the characteristics of C that would allow us to write Unix once, let's say, and have it run on two different architectures? Based on your understanding of high-level languages like C, what are the characteristics of it that would allow it to fulfill this goal? Okay, what does that mean? What does it mean for a language to be compiled?
It means there's an interpreter from the language itself to the CPU that it runs off.
So compiled languages, a compiler translates between high level and low level. So another way we can say that is a C compiler would translate between C syntax and native assembly. And native assembly could exist in several different formats. It could be assembly for the way back then. It would actually, that predated the x86. But, you know, let's say we have 2 or 3 different CPUs. There would be an assembly language, a language for each of those individual CPUs that would be different from each other. They might look similar-ish, but they'd be proprietary. They'd be different. So that would mean in order for us to write our operating system in C, but get it to run on all 3 of those computers, what would we need? What would have to happen for us to write an operating system in C, but have it run on those 3 different architectures? Yeah, we have to have the compilers would have to be ported, right? So all 3 of the compilers would understand C. They're all talking about the same high-level language, but their target language would be a different assembly language. So the first one would convert to x86 assembly. Another one would convert to MIPS assembly, something like that. Okay? That's the job of a compiler. Now, that sounds kind of foreign-ish, but isn't that the exact same thing-ish that Sun Microsystems did with Java? And they say, hey, rather than you having to write your program multiple times, how about we just write the interpreter multiple times? And it just targets this machine. They happened to write the machine in software, so the machine was less, the machine didn't change. So they wrote an abstraction layer on top of the machine. That idea wasn't a thing back then, and we've seen from in our talks about Java that that's been a performance hindrance as well, right? It's Java's downside is it's not as fast. Well, talking directly to hardware as fast as you're going to get. You know, now your slowdown is just how fast does light travel and stuff like that. Okay, so we have a reliance on compilers being written multiple times. Are all compilers created equal? Is there a such thing as a better compiler than another compiler? What does it mean for a compiler to be good? So you say quickly and accurately translates from a high level to a lower level? Okay. Do we necessarily, would we rather it be accurate or quick?
I suppose accuracy is the top priority, but if it's slow, then it's not a. I would say it's not a good
Pilot one is like speed is nothing.
Okay, so realistically speaking, we don't want compilers to be infinitely slow. But the speed of a compiler isn't all that important. We expect it to take time to compile a program. So the accuracy is much, much, much more important, with speed being secondary, let's say. What does it mean for a compiler to be accurate?
Efficient.
Okay, what does that mean?
Something like anything that can be a static variable would be, rather than having one static variable, where it would take that variable and implement it every time that it used it.
Okay.
You have to go back and make the extra call.
So let me get this straight. So you're saying that every Hello World program written in assembly doesn't look identical? There's more than one way to solve a problem in assembly, just like there is in all of our other programming languages? There's a such thing as a bad but correct solution and an efficient and correct solution? So would a good compiler be a compiler that translated high-level code into efficient, low-level equivalent code? Or you could have 5 compilers that all turn a high-level program into accurate, equivalent, low-level code, but they may not run at the same performance, because one of those compilers might do it in the easiest but least efficient way. Another one might actually really, really, really focus on creating streamlined assembly code. Something I probably said to you when we first talked about compiled languages is a sign of a good compiler is it makes bad programmers look like better programmers. Because they'll take relatively crappily written high-level code and turn it into, at the low level, indistinguishable from somebody who wrote pretty good high-level code. The low-level equivalent will be the same. All right, so as compilers have evolved, our need to be picky about the high-level code we write has reduced. That doesn't mean we shouldn't still be picky. It doesn't mean we shouldn't still be diligent, but we probably don't have to be as much. We've written, we've used the examples like in Java, we almost always use int, right? Even if we're only going to hold a number between 1 and 10, we'll still use an int. None of us use bytes or shorts in Java. But the compiler could certainly try to figure out if a value is not going to exceed a certain level, why not use the most efficient container for it? Leaving larger memory locations open on the CPU registers and stuff like that to do stuff when you do need larger values. All right, these are all...
would switch from an int to, you know what I mean? Like it would downcast your variables if it was pretty sure that you weren't gonna.
Well, let's say yes, but understand that at the low level, downcasting isn't a thing. Because we just have buckets we're putting bits into, right? And like, okay, well, I only need this many bits for the largest value this ever is, so I'm just going to use this hardware register because that's as big as I ever need, as opposed to using this other bigger one that would directly map to an int, let's say. But it's because we were lazy humans who just said, well, it's an integer. What are you holding? I'm holding a whole number. It's number 3. That goes in an int. That's where I put those. Where really, if we went back to the old days as a C programmer, we would have had to be much more careful about it because we needed to be good stewards of memory. And we were also dealing with, presumably, lower quality compilers. We probably guess that our compiler technology today is better than our compiler technology was in 1970. Fair assumption, right? All right. So, what does it mean for a compiler to be good? I like the little saying, make bad programmers look like better programmers at the low level. So it produces efficient and correct low-level code. Now, in the big scheme of things, for us in here at least, we're not really striving to understand the little idiosyncrasies of what makes a good compiler good and what makes an accurate compiler not so good. We care more about the way that these things are actually accomplished. We've all written plenty of programs where at the end we could look back and say, in hindsight, I could have done that differently, probably in a better way. So maybe the next time you write a similar problem, you solve it a little bit differently. Same thing will be true here for us. We're not going to focus on what's the most efficient way of doing things. We want to try to understand how we can wield the operating system as a weapon. Isn't that what that's what the hackers would do, right? Okay, the operating system, they bend it to their will. They're code slingers, right?
Hack the planet.
Hack the planet. Content cowboys. Console cowboys.
Is that freezing?
All right, so we want to try to understand what are those. If we think about communicating directly with the operating system as a skill, we want to figure out what our method to that method is for doing that, because we've come up during a time period where our operating systems keep getting better and better and better. From our perspective, what it means to the general public's perspective, what it means for an operating system to get better and better is to further distance us from the details. That be a true statement? I mean, could you sit down at a computer today and never see scary DOS prompty looking stuff? It's very common, right? In fact, one of our most popular, computers today, especially in like junior high school and stuff like that, these Chromebooks. There isn't a such thing as a terminal unless, and that's why these things have popped up. Like I mentioned, I think, did I mention it in class or was it somebody before this? The Cloud9. I don't remember if I mentioned it in here, but there's all sorts of companies that are doing hosted Unix operating systems, hosted Linux operating systems, where you actually interface with another operating system through a web browser. So you actually can get a console through a web browser, but it's not running on that computer. You're actually talking to the hardware on another machine someplace else. But punchline for what we were just talking about is this idea that we certainly are moving away from the nuts and bolts of our operating systems. That's the direction technology is going. Well, what we're going to try to do in here is go the other direction. We're going to kind of duck under the hood and get down near the hardware, kind of at that level where the operating system specifically talks directly to the hardware and try to understand what's happening down there. And by us understanding what's happening down there, we might be able to do some stuff that we didn't really realize that we necessarily could do before. It's maybe things we've heard of. We didn't necessarily think that, that's something I can just do with my computer. You've been using all the high-level tools up to this point. You haven't bypassed those. Think about it from at home. If you have a blender, the blender has a plug-in and has buttons on it, right? That's how the blender was intended to be interfaced with. But could you open up the blender and get into some of the wires and stuff like that and possibly do some modifications? Certainly a possibility. Okay, so the only way to interface with something isn't necessarily through the provided interface. That was the intended use. Okay, so we're going to open up some blenders.
How did you break the blender?
All right. So, What does standards mean to you?
Something I have none of.
What's the definition of a standard, just in general?
The minimum requirement to
A baseline for something for it to be
Okay.
good.
Minimum requirement to be part of a group?
sure.
Okay. So, give me some examples of some standards.
Like beef quality has standards.
Okay.
No, we already established that's none.
All right. So, for instance, boys and girls. Okay.
Fair.
There
and
are
good.
certain things that make you in one category. There are certain things that put you in the other category. Okay. These are standards. All right. They're around us. They're not just in technology. They're all over the place. All right.
My preference for goats.
Exactly. Why do we have these? What do standards allow us to pull off? What's the purpose of these?
So that somebody can pick up where somebody else left off.
Okay.
More easily.
Okay.
So that
It's
everyone
like
in a
learning
group.
standards where in high school and everything, the state sets standards and then basically everyone learns basically the same thing but maybe in a different way.
So there's a
And I think that's kind of what you're saying, right?
Yeah.
It's that you could make this assumption that when somebody comes out of high school, assuming wherever they went to high school, it met the standards fictitiously, right? That they are then starting at an equal footing with everybody else who came out of high schools that met the same standards. That's the theory. Okay, doesn't always work, but that's the attempt. Okay, isn't there also a compatibility thing? So, for instance, what if the plugin for our devices wasn't a standard?
Well, then you'd have Apple.
That's like wasn't it Europe who just like passed the law that
Which
all
one?
USB like
Mhm.
C types now have to be the same?
Yep.
Phone chargers like that?
But I'm just talking about the power plug.
That's the technical.
Yeah. What if our power plugs weren't all the same? All of our outlets look like this, right?
Yeah, you'd have to have a converter for all. of
Yeah.
these.
You have every single device you buy has to come with a converter so that you can plug it into the wall. But instead, we've accepted a standard to it makes things more convenient.
End up walking around with these.
Exactly. From the Amish guy. Why does the Amish guy have a power adapter? When in Rome. All right, so standards are there to give us a consistent experience across something, right? So we have a consistent experience across all outlets in the United States. If you travel over in another country, some other countries don't use the same outlets, like many other countries don't. So there's actually kits that you can have a bunch of adapters. So then you do have those types of things you have to pack. But what's actually happening in a lot of foreign countries now is they're just adapting to the Americans. No, it's what's happening. You know, it's a tourism type thing. Like, okay, well, we're going to give them their normal toilets and give them their normal outlets, and then they'll give us their money.
Doesn't Amish need the gerbil wheel adapter?
That would be pretty funny. So that's why we have standards. What does standards mean for an operating system?
Gives it certain ways it'll react. to input.
Okay. Well,
Certain
what is an operating system? Let's remember back to our 350 days. Some of you maybe only had it last semester, but many of you had it last year.
Where the user communicate with the hardware.
Okay. So now are all of our operating systems standardized across the board? Do we communicate with our hardware the same on a Mac as we do on a PC?
Security standards that they.
Yeah, I mean, based on what we said a few minutes ago, the real answer is we don't know. We're abstracted so far from that level that we don't know. mean, clearly the two user interfaces take different approaches, right? But that doesn't mean that they're not following the same standards at some level, maybe at many levels. So somewhere in there are likely standards that are being followed. So for instance, some of you in here have Macs, some of you in here have PCs, but you're all theoretically on the wireless network. I had to plug in the hardwire in my office earlier. It was zigging when it was supposed to be zagging.
Even slow today.
Yeah, well, but so the punchline is are we all on the same network? Getting Facebook notifications apparently. I thought notifications turned off automatically when you were on a. Doesn't matter, whatever.
Facebook said no.
So, several of you who are on a Mac are on the internet in here. Others are on a PC, they're on the internet in here. Why? Because the standard, the IEEE standard you're using for wireless has nothing to do with Mac or PC. It has to do with a wireless standard. 802.11, whatever, right? That's one of the evolving standards. What are we on right now? Probably
AC.
AZ.
They
Okay.
got a newer one.
Yeah.
It's gonna be like 10 feet away from it.
Yeah, every 15 seconds they come out with a new. It's like, well, this one's faster but doesn't have the range. This one has the range but it's actually not as fast, and whatever. And then the next one after that is it has the range and the speed.
Yeah. The current
Next thing you know, the wireless technology be microwaving stuff. Like, you don't want to go in that corner.
You want to make popcorn? Just toss the bag there.
Wireless single strong over there.
It's called a dead spot, but it's got a different meaning.
So, so these are all standards that allows us to have devices that can go into environments like this and operate. Even though these devices are different, they can all operate using the same standard communication channel. Okay, we all breathe oxygen, so it's a good thing that we're in an oxygen-rich environment. If we didn't breathe oxygen, if Large in here had gills, which jury's out, he would be having trouble. We hear him up here gasping and gurgling and stuff like that. All right. What's this? It's like, or he's a smoker. One of the two.
You know I don't have gills.
So, the idea here is that standards are very, very important. And it gives us a consistent way for us to experience a certain environment. So, would it make sense for an operating system to have standards? Okay, what kind of standards might an operating system have? We got to go back to that question I asked a few minutes ago about what is an operating system. What are the key features, the key things that an operating system does for us? A couple of you had 350 just last semester, right? Okay, we got process management. Fair enough. Resource allocation, memory management, that kind of stuff. Really, an operating system, in a nutshell, you could say an operating system is a resource allocator. That's what it is. So you have your whole computer is just a collection of resources. How do we allocate them? So process management, memory management, file systems. So it provides a mechanism to talk to jump drives, floppy disks, whatever. All sorts of different I/O type devices. Networking stuff. These are all things that an operating system should provide for us, right? Now, in the early operating systems, likely this stuff was written in a proprietary way. If we didn't already know, how we didn't have this power plug thing. So let's go back to the days of Nikola Tesla. No wonder that guy had that haircut. So, he didn't have these nice little plugins like this. He basically was just harnessing just brute electricity and trying not to kill himself at all hours of the day. And he didn't have a nice plug. He just had exposed wires. He would just walk up to something, see what would happen. Okay, so we start having standards to allow things to happen more easily. So let's just talk about networking. Since we were already talking about wireless and things like that, what kind of standards exist in the networking world? that would then obviously translate into our operating systems, because all of our operating systems seem to be network aware today, right? None of you have a computer that doesn't know about the internet? We all got one of those, right? Even the Amish guy. So what are some of the network standards that you're aware of?
The Wi-Fi like 802.11 B or whatever. Yeah, that.
Okay, so 802.11.
Yeah.
Okay, so that's how your network interface card in your laptop knows how to talk to the wireless router thing over there, how the bits are sent back and forth, right? That's the, we're not in control of it. All we know is the operating system talks to that device talks to that device, and they all kind of talk to each other, right? Okay, so that's a standard that exists. But how does your operating system talk to that device? How does it say, I want to send this email? Okay, so the driver, so software driver, for those of you who've had some of the programming classes, which should be all of you, notice that I often call our main program driver. Okay, so what is a driver? When we say a hardware driver, we talk about a driver. That's a piece of software that tells our operating system how to communicate with another piece of hardware. So you might get a brand new NVIDIA graphics card. You spent $1,200 on a graphics card. You plop it into your computer.
Driver compatible.
Okay, and what's it going to look like initially?
Horrible.
Yeah, 800 by 600 resolution. If you're lucky, you'll have color. Have you ever had that experience?
Yeah.
Like a really expensive graphics card, you plop it in and it's grayscale? Like, come on.
4K black and white.
Why is that? Because your operating system came with a standard driver for something that knew how to talk to a VGA compatible, actually if it was black and white it would have been a VESA, V-E-S-A, compatible display adapter. Okay, but whatever. So it said, I don't know what else this is, but at the very least, it has these 4 functions. Show these 4 colors. All right, that's all I know how to do, 4-bit color. Until you install the patch. You install the NVIDIA super duper driver that says, oh, I recognize this as the $1,200 graphics card that you just bought 5 minutes ago. Here's all the extra crap that it can do, and this is how it accomplishes it on top of the VGA standard. Make sense? That's what a driver is. Just a piece of software that explains to the operating system how to talk to the hardware. What did we do before drivers? Have drivers just always existed?
Just had to be on there already.
Yeah. What's nice about a driver? Yeah. Most of us have probably installed a driver on our computer well after we installed the operating system on our computer, right? If we didn't have this idea of a driver, wouldn't everything that our operating system knew how to do have to be there the day the operating system came out? Yeah. That's Unix. Less so today, but definitely early Unix. Oh, you weren't playing video games on Unix or Linux for a long time. Why? Well, you were talking to a monochrome screen. That's the driver it came with. Don't waste your money on new hardware. It won't work. Especially in the early days of network standards. That is, there weren't any. And even when they said they were, they only partially implemented. That was a big thing with sound cards for a long time. The sound cards, you would put it in and it wouldn't work. And it was because to save money, the company would, the sound card was like 3/4 software. And the driver was built into the sound card. But unless your computer had a certain feature on the PCI bus, it didn't know how to grab that software. It's like this is how it used to be. We just don't have those problems anymore. we hit and miss. We have weird stuff that still happens, but in general, we don't have these standard issues because we have standards. So drivers exist so that we can enhance our computing experience after the operating system came out. It allows our operating system to evolve with the rest of the world rather than us having to come out with a brand new operating system every single time a new graphics card comes out. Makes enough sense? All right. Well, why don't we just come out with a new operating system every time a graphics card comes out?
Takes so much time.
What's our favorite file system? Everybody in here should have a favorite file system, don't they? Well, what are our options in here? So it's going to be probably NTFS, FAT32, or
Apple Journal.
UFS, Macintosh. HFS is actually the Macintosh one. Basically it's a journaling Unix file system. Okay, so if you use a lot of external USB drives or jump drives, FAT32.
Universal.
Okay, works on both machines. NTFS, Windows only. HFS, Mac only. Then you got some experimental stuff between the two where you might be able to write to an NTFS drive on a Mac without horrifically disfiguring your drive.
Is it Linux? A lot of Linux exFAT?
I don't think so.
It was almost exFAT completely now.
It's possible. I guess it's possible. I haven't used Ubuntu in a while, but last I knew, all of them were running a journaling.
Yeah, exFAT's journal.
I don't think so.
Yeah.
Well, it's possible. It's possible. I don't know.
I kind of want to ask Siri that.
So, but in any case, has your favorite file system changed a whole lot in the last 2 weeks? Last 6 months? Last 6 years? So there's large portions of what an operating system does that doesn't really change very often, right? I mean, why fix it if it's not broken? Okay, so some of these things the operating system is providing: process management, file management, operating systems, the file system itself, memory management, the file system itself. These are all things that, yeah, they could evolve over time, but what does it mean for it to evolve over time? Maybe there's a couple of additional system calls. Okay? Maybe they update the way that a certain call functions in the new version of the operating system because the old one had a security flaw, something like that. But we're not talking about huge, huge, huge changes. Okay? For instance, Abe, how long has the fork system call been around? Long time. Long time. And they haven't changed it in a long time. Okay, forking today is just like forking was back then.
That's right.
So, this allows us to separate this idea that new hardware is going to come out that will augment our computing capabilities, and it allows our existing operating systems to talk to that. So, one idea of systems programming would be, how do I write device drivers? How do I create that middleman, that piece of software that lives between the hardware that just came out 5 minutes ago, that I plugged into my USB drive, or USB port, and the operating system that came out 5 years ago, that had no idea this guy would ever exist? How do I write that software? In terms of what tools am I writing that software? So most of us in here can kind of conceive the software itself, right? We can kind of think, okay, it makes sense that a piece of software would have to do the translation. You know, this guy was written 5 minutes ago, created 5 minutes ago, so he speaks language ABC. This guy speaks language XYZ. The software has to translate between those in order for this guy to function. And sometimes you don't even get the full functionality out of it, right? You know, those of you who try to play some of your video games with third-party controllers, sometimes you can't make all the buttons work. Sometimes there's a weird driver on Linux or something. Usually it's on Linux that not everything will work for that controller. Okay, but it's not because the controller's crap. It's because the driver isn't fully implemented. The controller knows how to do 30 things. Driver wrote 22 of them. Okay, somebody's got to come along and write the 8, or you don't get to use them. One of the two. Make some sense? All right, so next time we'll start off by talking about this idea of POSIX. So POSIX has gone through a couple of different iterations. What I would encourage you to do for next class is read chapter 1 from the book once it comes in the mail. It's not very long. It's only about 20 pages, 18 pages, something like that, chapter 1. It gives you kind of the history of Unix, which is the stuff we're talking about right here. Okay? So we'll come back next time to talk about POSIX. Also, the first homework assignment is up. It's the Slack thing. So nobody make me give you a 0 on that. Join Slack, join the group, post your stupid crap, take a screenshot, and submit it. I will see everybody on Wednesday.
See you Friday. I'm going to Vegas.